All right, welcome to lesson 13. Lesson 13 in EE 301. We're changing topics now after the first exam to move on to alternating current. That's what we see right here, alternating current. So everything that we've been doing so far is we've been looking at DC or direct current. Usually batteries are the voltage source. Well, now we're going to move on to alternating current or AC sources. Now note that these will have a lowercase, and the reason why is because they're changing over time. As you can see by this graph at the bottom, over time, if this is charting something over time, it follows a sinusoidal equation. That's why it says Intro to Sinusoids. So dig out of your brain there the old trigonometry stuff as we do a review on sinusoids. But first, let's just talk a little bit about what's happening. So we're used to the current coming out and flowing down through a circuit, and now it's going to go back and forth. The way this works is it's actually a magnet that's creating it. And so there's a magnet moving inside a coil of wire, and this magnet inside a coil of wire sends current flow back and forth. Whereas before in DC, it was just moving in one direction. With AC, it moves back and forth. But what makes it still provide power is that it's moving actually so quickly. So if I was looking at our circuit simulators here, so if I look here at my circuit simulator, so far we've had DC sources, and I close this switch, we can watch the charge move around the circuit. If I change that DC source out for an AC source, I can watch the charge go back and forth, back and forth. And actually what it's doing is it's moving along a sinusoidal wave. And at the bottom, we can see it moving over time. It's moving back and forth upon this sinusoidal wave. Every time that it stops, we see that that's where it's crossing zero. That's when as it moves, it stops, and then it accelerates and goes back. And it goes back and forth and back and forth. So that's what we're doing inside of here, is it's moving back and forth, and it's creating this sinusoidal wave. We have two parts that are changing upon this sinusoidal wave. The first one being lowercase e, that's for the source right here. And then we have lowercase I, and that's for the current. Once again, the lowercase because it's changing over time. So now let's talk about sinusoids in general. So this is where we dig out the trigonometry. But if we think of sinusoids, the first thing is just wave. And often we'll use this term waveform, and that just means this wave moving back and forth. And it goes through a cycle, right? It's crossing up through this time, through the x-axis. It's crossing up here, and it's crossing up here. That completes one cycle. So the time that it takes to complete one cycle is called the period. It's a capital T that is on the equation sheet. If we're looking on the equation sheet right here, everything that we're talking about today is in this top corner of sinusoids, and there is T right there. And T is the inverse of the frequency. So looking back here, F is the frequency, and it is 1 cycle per second. 1 hertz, 1 cycle per second, that is the frequency. So now that's one way to look at a curve, is looking at it a long time. Now let's talk about its height. Its height is called the amplitude. And there's a few terms about this. So the amplitude is the height from the top of the peak to the x-axis. Whereas the peak to peak voltage is right here, from the height to the valley, from the high peak to the low peak. And so it's always the peak voltage is E peak is always E peak to peak. That's always true because it's always moving along the x-axis. So once we put in these two parts together, we can see the basic sinusoidal source is given as EM. Right here, that EM, that's the same as saying E peak. Right there, EM or E peak. and it's a sinusoidal wave. So we use sine, and then alpha. Now what is alpha? It's its angular position. So at any moment with time, we can look at the degrees that we plug in. If we were to put it in degrees, 90 degrees, and we can plug in the alpha. And if at this, for this particular sinusoidal wave, at 90, that's its peak. At 37, we could find a value of it. And so it's an equation along this waveform. Now, the way that we use it in this class is we actually put it into this form right here with omega t. And so for pretty much forevermore, we're going to say the angular velocity right there is omega. Omega looks like a W. Actually has a little circle there. Omega is the angular velocity. And what it's doing is that is just converting it from degrees into radians for us. We can see pi is 180 or 2 pi is 360. And so this term is in radians. This omega t is in radians. What is the relationship between this angular velocity and the time? Right here, 2 pi f. That's also on the equation sheet, along with this equation right here. So if we look at the equation sheet, what do we have? There is angular velocity is equal to 2 pi. That's putting it in the radians with the frequency. And then we have the sinusoidal equation. This x peak is just saying right here that it's v or I. There is no x. This equation sheet is just a shortcut to say it could be v or it could be I. Could be the voltage or it could be the current. And so the x is saying it's both of those. The formulas work for both. So let's move down a little bit and talk about phase shift. Right here is the phase shift is theta. And theta is when this x-axis, when the graph, the waveform doesn't go through the x-axis. So previously, on this one right here, you can see where it's crossing up through zero at, it's crossing up through zero, the x-axis, at right here at 0 volts. So if it's not that, if at a certain time when it hits and it crosses along, sorry, I said 0 volts, I meant at 0 time, it has 0 volts. If that's not the case, then we have a phase shift. And the phase shift is just telling us whether it's a positive right here, and this is the key, a positive theta right here means that it is leading. Positive is leading, negative theta is lagging. So if we think that it's crossing at time equals 0 would be 0, well, we can think that it's a good thing to be leading, it's positive. It's a bad thing to be behind, it's lagging. Negative is lagging, positive is leading, and that will always be the case because we can compare two different waveforms, and I could say, how does theta I relate to theta V? Well, it depends on where the graph is. One graph could be leading the other, and it's the same with relative to 0. So if we just say a lagging waveform, we mean relative to 0, but we can also ask about the relationship between two different thetas. There is an equation to get this theta, and it's this one right here. That's also on the equation sheet. So the theta can be found by finding the delta t. So if we didn't have it in right here, is it's given as a theta, but if it was given as time, then we can turn that into an equation. So right here, theta is equal to delta t, the difference in the time over the period times 360, and that puts it back into degrees for us. So now let's actually just do some of these terms on an actual waveform. Now that we've kind of reviewed them, the first one is the peak voltage right here from 0 up to 8. So that one is 8 volts. The peak to peak voltage, I always said, is twice that, but you can also look at it and say from -8 up to +8, so it's 16 volts. The period is always the same upon a waveform, so you can pick whichever ones you want to pick where it crosses. Here's right there, I'll put it in green where it's crossing 0. And where does it go up through 0 again? Right there. at 0.4. So that capital T is equal to 0.4 seconds. If you wanted to put it in engineering units, you could say 400 milliseconds. So what is the frequency now? The frequency, F, is equal to 1 over capital T. That's 1 over 0.4 seconds. We must always put it back in seconds because that's what it means. The frequency is hertz, which is 1 per second. That comes out to 2.5 hertz. You can look at example 2 now. Determine the frequency of the waveform shown. So the frequency, lowercase f, f is equal to 1 over capital T. So let's find T. Once again, we can look at where it's crossing at a certain point. Well, in this case, I'm going to choose where it's crossing down through the x-axis, or down crossing through time. And you follow it, down, crossing right there. So what is that capital T, the period? Well, we were at 20. It is 20 because it's 25 minus 5. So the frequency here, and this is milliseconds, so be sure to plug that in properly whenever you're doing it, and that would be 0.02 seconds, and the frequency comes out to 50 hertz. We'll skip number 3, go on down to number 4. This one has a few more parts. Determine the waveform's period. I'll follow it up right there. That one is crossing through 0. Follow it. Where is it going through again? That's kind of by inspection. How close is that? You know, if we're just looking at that graph, let's call that T is equal to, if there's 40, there's 30, there's 25. So there's 22.5. It's in milliseconds. So now we can do the frequency. Time is equal to 1 over 0.0225 seconds. That's F. Lowercase f is equal to 1 over T. And that comes out to 40, that's seconds, 45 hertz. What is the value of Im? Well, this is a current, so that makes sense that it's I. And Im is the I amplitude, which is also the peak, which is just the highest point that the graph gets to. Right there, I can even see it, it's 60. So part C, Im equals 60 milliamps. Be sure to follow the units. In D, it's always twice that. So I peak to peak is equal to 120 milliamps. Do another example. Looking at example 5. And this one says it has a sine wave of 50 volts at when the angular velocity, angular position rather, the angular position is at 150. So we can even kind of see it from the graph right there. It should be something about like that. But we can just form our equation and then plug it into the equation. So E as a function, we'll erase that. We'll call it as a function of alpha. E as a function of alpha is equal to E magnitude, or E amplitude, sine as a function of alpha. So that's what we're looking at. And what we see is that at 150, so E at 150 degrees is equal to 50 volts. There's the amplitude, sine, make sure that we keep it in degrees, 150 degrees. So I can find the amplitude is 50 volts divided by sine 150 degrees, and I get 100 volts. All right, we'll skip number 6, go down to number 7 to look at the phase angle here. So here, it's not crossing through the x-axis, or it's not crossing right there. It's crossing a little bit before it. So before I even solve for it, I can tell that this is a leading, right? It's leading because it's early, it's ahead. That's a good thing. It's positive. And so that's a positive theta angle that we're going to express here. But what we need to do is solve for it. So first, it says determine the equation for the waveform expressing the phase angle in degrees. That's what we're going to solve for. Second, the first part that we need to find is the period, because we're going to use this equation right here. Delta t over t, that's how we're going to get the theta angle, times 360 degrees. T is equal to 1 over f. All I did there is take the equation, f equals 1 over t, and I rearranged it to solve for capital T, the period. The frequency is given right here, 833.3 hertz. And I come out with a period of 1.2 milliseconds. My delta T is 160 microseconds. So if I'm plugging that in, 160 microseconds over 1.2 milliseconds. If I'm typing that into the calculator, that's 160. You can use the button E to the negative sixth or times 10 to the negative sixth in 1.2 E negative 3 times 360 degrees, and I get an angle of 48. I can see right here, there's my amplitude is 100. So my sinusoidal equation, E as a function of time, is equal to that amplitude. Where am I getting this equation? As a reminder right here, E peak, that's the same as the amplitude, omega t plus or minus theta. So here's E t. My peak value is 100 volts. Sine. And then we have here omega t. Well, what is omega except 2 pi f? So we could write 2 pi 833.3 t, because it's a function of time, so time stays in the equation. And then we have a positive because it's leading plus 48 degrees. And there's how we find the equation off of analyzing a waveform. So earlier I discussed that we have leading and lagging as far as how it relates to zero, but we can also compare two waveforms. So these are in phase because they both cross through the, I'll put them in, what is that? I'll just do a blue. There's that one. It's crossing through zero. And then, ooh, that's really thick. Go this way. There we go. So they're both crossing through zero. Well, now let's look. Here is where V is crossing, and here's where I is crossing. Which one is ahead? I is leading, right? It's positive to be ahead. So if I was taking a delta theta here, say the delta theta, right? The difference between the two, and let's say theta V minus theta I. Well, which one is V is crossing through zero? I is positive. So that would be a minus theta I, right? And we could see here that there's a difference between them. Now in this case, current is lagging because it is behind. Here's current coming through here. Here's voltage going through zero. Current is behind. They don't both have to, no, one of them doesn't have to be through zero. We could do one over here, right there, and right there. Well, which one, let's say that the blue was I and the black was V. Well, which one is leading now? Well, V is leading I. Neither of them is going through zero, right? But V is ahead of I. So we could say V leads, or we could say I lags. Means the same thing. So here's a phase relationship between two different waveforms, like I just said. Neither of them is going through zero, but we can look at it. What is the phase relationship between them? I is crossing through the x-axis before V is. Therefore, I is leading. I leads V. And it says the phase relationship, so we need to take the full amount. Well, how much does it lead by? Right here is 80. Leads V by 80 degrees. Also note that they gave us the equation. So even if we didn't have the graph over here, we could look at omega t plus 60. That's like theta I right there. And negative 20 would be theta V. So if I needed to know their relationship, I do 60 minus negative 20, 60 minus negative 20, and that gives me positive 80. Notice that this one is leading, this one's lagging from 0. This is, you could say this is leading from 0, this is theta I is leading from 0, theta V is lagging from 0, so therefore it's I is leading V by their sum, by their difference there. Last topic is RMS values. RMS means root mean square. And the root mean square is just this idea of root 2. Right here, VRMS divided by the square root of 2. Often you'll hear us say divided by root 2. Divided by root 2. Root 2 is right there, RMS. And what this means is that if I had a sinusoidal wave over time, right, and I needed to do work with this voltage that I'm going to be looking at, well, under this waveform, at some point, the voltage is 0. Right here, when it crosses the x-axis, here's the voltage. Well, the voltage is 0 right here. The voltage is 0 right here. The voltage is at its peak right here, but it's changing. How frequently is it changing? If we were in a 60 hertz system, it's changing 60 times every single second. 60 per second. So 60 times within 1 second is how much it's changing. But at some point, 60 times within that, or either 120 times because it's going up and down, right? 120 times within 1 second, it's at 0. And 120 times within 1 second, it's at its peak. So what this RMS does is it takes its average power for us. And if you look at the calculus behind it, it's like we can put this in a box, and what's up here and these sides are effectively canceling out, and what's left inside my green little box is what's actually its ability to do work. But if you don't want to mess with the calculus, just remember root mean square means effective. RMS and effective are synonymous. Go back to the equation sheet, and that is also in here, right there. X RMS, meaning the voltage or the current. The voltage or the current, there is no X. It just means if we could take it out of this equation, so if we had a sinusoidal equation, we could take that peak, plug it in, divided by root 2, and we would get its effective value, or its ability to do work, RMS value. And with that, that concludes lesson 13.